Right, welcome everybody. So we are going to talk today about the perhaps I think underappreciated world of debugging, right? And we're going to look at various tools. I'm going to give little demos of things, and just a few sort of tips and tricks in that. And I'm going to try and cover lots of stuff at a kind of shallow depth. I think often it's easiest to sort of set the scope for things by saying what's out of scope. So what this isn't. So I'm trying to, as far as possible, I'm going to steer clear of generic advice. Frankly, I'd feel like I was being a bit patronizing if I tried to get there. So it's going to try and be specific and concrete. It's not about testing or testing tools. Like there are loads of really good testing tools and there are loads of really good talks on testing tools. This isn't one of them. I'm not really going to talk about how to avoid writing bugs in the first place, at least not much. And it's not about performance profiling. Again, loads of good tools, loads of really good talks. Check out Brendan Gregg, among others. Although, like, there is some overlap, right? It's not like performance, there is, you have performance bugs, and both performance and kind of more classical debugging are really an exercise in trying to find out what actually happened as opposed to what you were expecting was going to happen. So some of the tools work, some of the tools, particularly perf and things, can be good for both. So there's a bit of overlap, but generally I'm going to stick towards the, oh my God, it's crashed, as opposed to didn't quite go as fast as I was hoping. Certainly not exhaustive, right? And maybe if we get time at the end, there might be a bit of sort of audience participation, kind of crowdsourcing stuff about things that I've missed off that you found useful. And it's certainly not like a workshop, it's not a training. I don't expect anybody to come away having become an expert in any of the stuff I'm going to show. The kind of point is, like I said, it's lots of stuff at a shallow level. So the point is to kind of, probably most of it you've heard of, but maybe a lot of it you haven't seen. So it just gives you that sense of like what these things are, where to start, and essentially then you know what to Google for and you know what to read the documentation for, right? I'm going to try and give a little bit of context about kind of why I think this is important. I guess to some extent I'm preaching to the converted because you've all come to this talk. But if you'll forgive me 5 minutes on my soapbox. So yeah, isn't it better not to write bugs in the first place? Yeah, well, obviously, right? I think actually it's a good test to apply to how meaningful a statement is could you argue the opposite in any, and it be kind of it'd be reasonable, right? And clearly that's kind of an obvious statement and so an uninteresting statement. But unless, well, both you are perfect and you work with people and work on code written by everybody else who's perfect, you're going to have to debug the thing, and probably, let's face it, quite a lot. So here's a nice quote, straying dangerously close to generic advice, but it's not mine, so I think I can say it. So everyone knows that debugging is twice as hard as writing a program in the first place, so if you're as clever as you can be when you write it, how will you ever debug it? Anyone? I bet a lot of people have heard that quote before. It's well known. There's a few nods. Anyone know who said it? Kernighan, yes. Very wise man. Now, clearly, Kernighan's point here is keep it simple, right? And I think there's actually another bit of advice along this in this vein that I quite liked is that programmers are like motorcyclists or maybe drivers of like when they first get their license, they race around at 100 miles an hour, being as clever as writing the code as clever as they can, driving as fast or riding as fast as they can. And the ones who survive when they get into kind of middle age tend to drive around or ride around a lot more slowly, and they have that kind of that margin for error, right? Because they know that actually they are going to make mistakes or other people are going to make mistakes. Anyway, that's not why I find that quote interesting. I think actually it has implications if you take it to be true, that it kind of means that debuggability is the limiting factor of your code, right? So whatever metric you want for how good your code is, right? Whether it's how fast it runs or how small it is or how maintainable it is or how quickly you can write it or whatever the metric for good is, debuggability is the limiting factor. And if you can make debuggability, if you can get twice as good at debugging, then you can make your code twice as good. It's like the most important thing, or one of the most important things we can do, certainly the most, I think, undervalued things that we can do as programmers. And I think if you just stop to think about it for one moment, you know, I mean, you're looking in a system that's usually executing billions of instructions every second. Typically it's interacting with lots of other programs, more and more things that are distributed, or God help us, human beings who are interacting with the program, right? And you're looking for that one bad instruction, right? So it really is the ultimate needle in a haystack challenge. And if you're going to find a needle in a haystack, better to try it with a metal detector than just rummaging through, right? So another quote by Kernighan: "Most effective tool is still careful thought coupled with judiciously placed print statements." Very wise chap. I mean, certainly, you know, there is, you know, careful thought is really important. We've all, I'm sure, fixed bugs when we're in the shower or riding the bike to work or whatever it is. And there is still a place in the world for print statements for sure. But Kernighan said that in 1979. And I like to think that we've moved on a little bit in the intervening years. Right? And this is back when your print statement probably came on some kind of, you know, green text on black background teletype or something, if you were lucky. So let's look at how we've progressed and actually I think perhaps in the last decade things have moved on really quite a lot. So I think there are two. I sort of classify these debugging tools in these two classes of things. There's checkers, right, and for lack of imagination, what I've called debuggers, right. So checkers are essentially looking for instances of commonly made mistakes, buffer overrun, a memory leak where you forget to free whatever it is, right? And there are more and more of these. Some are free, some are paid for, and they're very good, right? And they tend to be very good at saying, there's the problem, or at least here's some way. Sometimes you have to kind of still go back to think, well, why did that happen? But oftentimes they'll just tell you, yeah, there's your bug on line 42. It's there, doofus. You've got an off by one error or whatever it is. So super cool. But of course, you know, as I said, they're looking for instances of well-known, commonly done bad things. Whereas the debuggers are more general code exploration tools, right? And they're just trying to get a sense for what on earth is my program doing. And that's really what debugging is, right? We write these programs with a certain expectation of what they're going to do. Reality diverges from that expectation, as so often is the case, and we need to kind of find out, well, where exactly did reality diverge and why? So I'm going to talk about both of those things today. So here's a rough schedule of what I want to cover. We'll see how we go. I've done this talk only once before, and the timing looked nothing at all like that. Maybe we'll get closer to it this time. So I'm going to split like a lot in GDB, but maybe about a third in GDB, and then we're going to look at all kinds of other stuff. And I want to talk about GDB because, you know, obviously it's been around for a long time, but it's come a long way. Actually, it's had quite a lot of active development, particularly sort of 5 years ago or so. And I want to show some of the things that it can do that you may not be aware of. So I'd say, you know, there's this difference between easy to use and easy to learn. GDB definitely is not easy to learn, but once you know it, I think it is quite easy to use in that you can use it to do what you want to do. So let's get into some examples. I'm going to kind of do a lot more of this sat down now. But right, so apologies to anyone who's seen one of these talks before, because you will have seen this stuff. But a lot of people still haven't seen it, and it's still really, really useful. So here's my not much more than hello world program. So I noticed I called it debugging in C++. It's really not, the language isn't important actually. It's more like debugging compiled code, I think is the should be the talk title. But most of the examples are in C because it's just simpler. Anyway, right. So let's run my program, and I'm going to run it in GDB. So this is the GDB TUI. It's called Text User Interface that I want to show. So, well, surely you'd think GDB is always a text user interface, right? Here we are. Start just puts a temporary breakpoint on main and then does a run, so it's just slightly less typing. Here's my program. I can type list. it's all feeling very like Kernighan's 1979 world, right? This isn't the text user interface. This is the command line interface, the CLI. If I go Control XA, I'm going to the 2E mode, which is all nice, beautiful cursive stuff, right? But actually, like simple and kind of ugly or whatever you want to call it as it is very useful, right? And it means you can just be SSH'd into wherever you are, and you can just do this, and it all just works nicely, right? And so I can do the usual stuff, and I can print I. And now the only thing that often happens with one of the ways that GDB can go weird is if you do what I've just done here, the default thing of just starting GDB and running the program, your program, the debuggy, or what GDB calls the inferior, is sharing the TTY with the debugger, right? And that can lead to bad stuff happening. So if I just step or next over that, I should see, oh look, it's actually, I wasn't expecting it to go in quite that way. So it's just done a weird thing. I can Control L, and that will just repaint the screen and get back, and that gets you out of trouble most of the time. It is built on cursors, so sometimes it does just go mad, and you just have to, sometimes you just have to restart. But I personally spend a lot of time these days in this view, because it mostly just works and is simple and does what you need. You can get kind of a many windows view. So if I go Control X2, I'll get more windows. So now I can look at my assembly code as well. And now one of the things that caught me out with this when I was first using it is if you go up arrow, that's usually you'd expect up arrow in GDB to give you the previous command, right, to save you some typing. But it just moves my view of the world up and down. So I need Control P and Control N to go back through my command history, right? And likewise, Control A to go to the beginning of the line, Control F and Control B to go back and forward. Because if I try and use the cursor, I get that. But that's the sort of thing that once you know it, it's fine. When you don't know it, it's a pain. I can cycle through these, I think, so I can say they're my registers. Now I'm going to go Control XA to get back to the kind of classic view. Now, there's another thing called GDB Dashboard, which is very clever, and it's basically just a GDB init file. So I can source it if I can remember where I put it. I think it's in here. And that gives me this view, which is kind of 2E-like. And here I can see it doesn't show up brilliantly on the screen, but we can see the line 9 is highlighted there, and I've got various of my bit of stack and locals and everything else. So if I do a next, we'll move forward a line, and the registers update and everything. So that's quite useful. I know I don't tend to use it that much because it's a little bit too much information in my face, but I know people who use that quite a lot. So GDB Dashboard, it's just a GDB init file. You can download. Let me come out of. So it just looks like. That's not what I wanted. So it's lots of user-defined functions, lots of Python. We'll talk about that in a bit. But here's some of the cool stuff you can do with the Python that's built into GDB. So there we go. So 2E I think is useful as it is poorly named, and it can actually just gives you a lot more context of where you are. Let's talk quickly about the Python that is now in GDB. So I just referenced that. So GDB has Python in it these days, has done for a little while. It gets increasingly, it's developed quite actively, so more as time goes on, you get more and more of the kind of binding between Python and GDB. So let's just have a look at what some of that looks like, right? So if I start, let's do my really simple program again. Let's go into 2E mode because that just makes it easier to see what's going on. So I can go Python, I don't know, like print hello, right? And it'll run that Python. I can execute GDB commands. So if I go, well, I can go like a Python, I can import GDB, and then I can go gdb.execute, and I can just give it a command to execute, and it will do that. I can pull the information out of my debug quite easily. So parse and eval is kind of a mouthful, but so I can go GDB parse and eval I. Well, it probably would have been better if I'd gone, sorry, parse and eval I print I. Okay, so you can imagine how you do various things with that. Now, of course, that's just I. My Python program still maintains its state, so Python print I is still there. Of course, one needs to be careful, because if I go like, oh, look, it's messed up, Control L, I go like that, then print I, now I is 2, but of course, if I go Python print I, that's the I in the Python context, of course. And yeah, okay, so, and then if you want to know more, well, this is, whoops, Python help GDB, and that gives me all my lots of things you can look at. Breakpoints, for example, is quite good. So you can create the breakpoint just through some Python code. You get this breakpoint object. You can look at like the state, how many times has it been hit, like is it enabled, all that kind of stuff. Python pretty printers are quite useful. So you must be able to make this work in with a bit less typing than this, but this is it works. So let's look. If I have so I've got a really simple program which contains a structure, right? It's a student structure, as is popular in these sorts of things. So let's compile that, and let's load that up to GDB. So here I am, let's go over, so it's initialized. Okay, so print stir, let's do that again, print stir, well, okay. Now that's, actually I've got pretty printers on by default, so actually by default, it'll be set print pretty off, and if I print stir, it looks like that. So I'll just show you, by the way, so this is, I said I wasn't going to do any generic advice, but here's a little bit. I advocate a very simple GDB init file. I've had too many problems over the years, particularly from customers who have all sorts of weird stuff in their GDB init files. People putting a run in their GDB init file is not unknown. Like you can just type enter if you're that averse to typing. And of course, like I did with the GDB dashboard thing, you can just source what you need to source. Often it's good you can put these things in your Git repo or wherever and just source them. Anyway, but print pretty on I prefer. So right, so what were we saying? So print student by default do that. Set print pretty on. Okay, gives me a bit more, but still not great. Let's have a look at that's the pretty printer code I just showed you on the slide. So if I source that, and now when I print, it gives me in a nice kind of human readable format and passes the date and all that stuff, right? So yeah, pretty printer's a bit fiddly, but you just copy and paste and you can get that stuff working quite easily and then can be very useful. With modern distros, GDB has a bunch of pretty printers for STL, which is good, right? But one thing to be aware of is that the pretty printers come with your GDB and whatever, like as long as you're using the STL like dynamically loaded from that machine where you're running GDB, then it's all good. If you start to kind of take, some kind of a version of GDB that was built on another machine, this is quite a common thing. So someone builds a version of GDB on another machine, and in the old days, this all worked well because GDB was just a it was just a binary, right? An executable, and you could ship it around and it'll just run wherever, as long as nothing bad happens with libc. These days, not so much, because there's all the pretty printers and everything else that kind of come with your GDB installation. So if you copy that GDB around, what you'll find is your pretty printers for STL will be mismatched with your STL on that system, and so that it tends often just to be unhelpful. It might sometimes print you the raw data. It might just print you nothing. So if your printing STL stuff doesn't do what you want, that's probably why. The other thing, likewise with the Python, actually. So if I can just go back to the Python stuff. So it's the Python interpreter is built into GDB, but you can import all the modules from the system. And so again, if you compile your GDB on one system and copy it somewhere else, then likelihood is that the Python is mismatched with the system libraries, right? So I can go like Python import os print I am pid which, so it's not actually important to notice. It's not shelling out, right? The GDB PID is that 10928, right? So it's not shelling out a process to run that Python in or anything. But I've imported OS. Now this is the GDB from my system, so I've imported the OS module and it all works. I've had numerous bug reports from customers for our stuff where they've said, well, because we rely on the Python, and they said, well, the Python's working. Look, I can do simple Python commands, and I can even probably import OS, and it just works. And then you just do something a little bit more funky with the modules on your system, and it doesn't work in weird and wonderful ways. So yeah, just sort of beware of that. GDB now, it's more powerful, but it depends on more things on your system. I talked about the keeping the GDB init file simple already. This is quite a cool thing, right, to have that in your GDB init. So it means that when you up arrow or control P to get your command history, it remembers it across GDB sessions, right? So that's often save you a bit of typing. And has nothing, of course, to do with any kind of reversible debugging or any of that business. This is your command history it's saving. Pretty printing off, we spoke about pagination off because it just, I find, gets in the way more often than it helps, and confirm off because if you're not living life on the edge, then you're taking up too much room. Just a little bit about how this stuff is all implemented, because when stuff gets funky, it can be quite useful to know what's going on under the hood, right? So GDB is built on this thing called ptrace, which is a pretty ugly API inherited over from, I think, Solaris. There have been attempts in the past to replace the ptrace API on Linux. They've all floundered, not actually made it. I think it's probably the lesson there is ptrace is kind of ugly as an API, but not many people need to program to it, and it basically works. So GDB will be ptracing the program. There are two ways this typically happens. One is you do what I've just done in all the demos so far, which is to type GDB and then type run or start, so that the debuggy is actually an inferior, it's a child process of GDB. And ptraces that way, or of course you can attach to a running process, which if you're as advanced years as me, then you might remember that it didn't used to work very well. If you haven't tried it in recent years, it works pretty reliably these days. Attaching to a running process, that is. The only thing is, on some distros, notably Ubuntu, they turn off the ability to ptrace attached to another process unless it is a child process of the ptracer, using this oh gosh, what's it called? Yammer scope thing. So it's this kind of seen as a security threat. Clearly, it is a way that you could launch an attack if you could get onto the system in question, and then you can start to ptrace attached to whatever process is. So you have to disable that. It's a sysctl thing, or you can just poke it into the proc file system. So I have it, I think, yeah, I do that, which enables me to attach to a running process. Anyway, in either case, it's using ptrace, and then it's all signals, right? So how ptrace works is you're tracing the tracee process, so GDB to a.out or whatever it is, and ptrace allows the tracer to continue that process, and then when it receives a signal, the tracer does a wait or wait PID on the tracee, and when the tracee receives a signal, the tracer is notified about that signal through the wait PID result. And then the tracer can decide whether to pass that signal back in when it continues it or not. So if let's start. So is it show handle? How do I do that? Yeah, okay. So this is the default way these signals are set up. So for all my signals, when the debugger receives a signal, does it stop? All right, do I get notification of that? Does it stop at the prompt? Does it print? Does it give me notification that signal has happened? And does it feed it back into the program when the program is continued, or does GDB kind of swallow it, right? And so for most of them, it's like yes, yes, yes. But you can see there are, and you can change all these defaults. But one thing probably, let's look. So sigtrap is a bit different, right? So sigtrap is the signal that your program will receive when it hits a breakpoint or you do a step high, which you can do through ptrace. So the program receives a sigtrap. GDB gets notified of that receipt of that signal. When it continues, it doesn't pass that sigtrap back in because that will probably terminate the debugging, and that's not what you want. But if you really know what you're doing, you can configure it to do so. The other one to be aware of is sigint, and that one up here, signal 2. And that said it won't pass that in. Again, it'll probably terminate the program. So when you run the program in GDB, you hit Control-C. Now, in that sort of default mode where you're running your debuggy within GDB, they're sharing a terminal. So when you hit Control-C, that actually gets interpreted by the TTY machinery inside the kernel, which just delivers a sigint to all of the processes in the process group of which the terminal is the controlling terminal. I think it's a language or something like that, but it basically means the process gets a sigint, which then GDB sees, and then GDB can decide when you continue whether to pass that in or not. And by default, no, but sometimes your program might rely on those sigints, and life gets pretty tricky if that's the case. Okay. So that's how that stuff's all built, and I think generally things probably work better when you attach to a running program because you don't have all this pain of the shared TTY, and GDB when you continue the inferior will then have to give sort of ownership of that terminal to the inferior, so that when you type input, it goes to the inferior, and it just gets all a bit of a mess. So if you get basically if you find weird terminal issues, then try attaching is perhaps a useful way around that. How are we doing for time? So very quickly then. So watch points, very very useful feature. They're built now. The original implementation of watch points in GDB preceded the CPU support for them. So if you set a software watch point and then you run the program, what GDB will actually do is step high, as in single step, every single instruction, and check whether the thing you've watched changes. And that's almost certainly not what you want because it's super slow. Interestingly, you can watch a register value and it will just do that for you. It's always a software watch point. So I can show you what I mean by that. Like I can go, so info break tells me what breakpoints or watch points are set. And if I can go watch like RAX. It says, yeah, sure, put a watch point on there. Now, notice that's different than if I go watch, oh, hang on, where are we? Have I started yet? Oh, hang on, right, let's disable that. Disable 2, let's put breakpoint on main, continue. Right, so, and then, so if I put a watch now on, oh, right, okay, so let's say I'm going to put a watch on st.id. Right. So notice the subtle difference. It doesn't really shout about this, but I've got watch point 2, I've got hardware watch point 5. So the hardware watch point is using the CPU machinery. x86 will support up to 4, and it will just run it at full speed. And when that location in memory gets modified, the processor gets a trap, and GDB will be notified and it'll stop you. So it runs full speed until the thing changes. You can. It's reasonably smart. So if you watch like pointer points to thing, it will actually watch the pointer and that offset in the structure that it points to thing. So that if pointer changes, it will. Now the other thing it will do, which can catch you out, is, and this, if you think about how this was originally implemented, it kind of makes sense. So if you remember, the original software implementation in GDB was step, 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 check, check, step, check, step, check, step, check. So when you run in the hardware mode, if you write to that location in memory, the CPU itself will trigger the exception, but GDB will then take a look, and if that location hasn't changed, like say if it contained 42 and you write 42 to it, GDB will just go, oh, that was kind of a false alarm, and it will continue, right? So usually that's what you want, but sometimes it can be surprising. Just watch out for those subtly in place software watch points. It will also put software watch points if it decides it can't use hardware watch points, which means, register. You can't do a hardware watch point register, it'll do it there. But you might be watching some large chunk of memory that's more than a single word. Sometimes GDB will place multiple hardware watch points adjacent to each other. Sometimes it will use a software watch point, like just depends. So just watch out for that. I don't know of a way to tell GDB don't use software watch points. However, if you just have too many hardware watch points, because the CPU only supports up to 4, then it will just say, oh no, I can't set that. It will try to set hardware watch points. If it's simply too many, it won't fall back to software. It will just refuse to set them. Remember I said that if you watch like pointer points to thing, it will put watch points on both, and it also will put a breakpoint on the scope where the thing you're watching goes out of scope, and then it will disable that watch point. So particularly with C++ type things, you've got someone stomping on your thing on the stack or something, and you've got no idea where that's coming from. You probably want watch-L for a location watch point, and then it'll just watch that address, and it won't try and be clever about not watching it anymore if it goes out of scope or whatever. Older versions of GDB didn't support watch-L. You could fake it quite easily by just taking the address of the thing that you're watching and casting, but watch-L is just a bit more convenient. If the CPU supports them, which x86 does, you can have read watch points. You can have watch points being specific to a thread. You can have watch points being conditional. But you can have the same for breakpoints as well. Breakpoints can be specific to a thread, and breakpoints can be conditional. So it will only stop when the condition specified hits. Of course, the program will stop every time. If you set a watch point like this, the program will stop every time foo is updated, and control will go back to GDB, and GDB will decide whether the condition is true, and then it will continue if it's not. So if it's like inside some really tight loop or something, it will go very slowly, right? Because there's all those context switches between your program and GDB. If you're using remote debugging, which I'm probably not going to get time to go into in too much detail, but you can, of course, as you probably know, you can connect GDB to a GDB server over a socket or whatever, and debug another over another system. And you can use these things called agents, which will do that condition check entirely on the remote machine, so that you don't have to ping bong back all the way to GDB across the wire. So that's much better. It's still gonna have a lot of context switching, but at least it's only within one machine. Thread apply is quite useful, although if I'm honest, I think I've only ever seen it used in anger with that. Get a backtrace and possibly backtrace full. Backtrace full will give you all of your threads. so I've got here a little threaded program that does that. So if I run it in there, and so I can go info threads gives me all that. So if I go thread, what was the thing? Yeah, thread apply. But I could go, thread apply 1 to 4 print stack pointer, right? Or I could go thread apply. This is when you really don't know what's going on, and this is often a useful thing. Thread apply all backtrace full, and it gives all my threads and all their local a backtrace for every thread with all the local variables from every stack frame. So that can be quite useful if you're trying to get that information back from someone's reporting something that you can't reproduce or whatever. Okay, dynamic printf is quite so. Yeah, so printf is like it's the lamest way to debug and all that. But actually, let's face it, it is kind of useful, right? It's probably partly because I think part of it is probably just cultural, and like every programmer will just be used to that. That's how they started, and we all just know how to do it, and it's very kind of automatic and effortless. And if you know the thinking fast and slow, it's system 1 rather than system 2 stuff. That's the not good reason, but the other good reason is it's often just really good to get a high-level view of like what's going on. The problem with printf, of course, is that when you need to get more information, you need to recompile your program, right? We all, obviously, you find, okay, printf, the value of foo is not what I expected. Oh, but that's because it's based on bar. What the hell was bar? I need to add another printf. So dynamic printf lets you do that from within GDB. So in my threaded program here, if I go, I'm going to restart it because it's probably run out of time. So if I go dprintf and I give it a breakpoint syntax. So what's going to happen under the hood, of course, it's going to put a breakpoint here. Now the syntax here is kind of horrible. You have to do commas without spaces so that it gets passed in the GDB machinery as like one argument to the dprintf thing, and it'll parse it. But anyway, so mutex is %p, and then I can go magic is %u, and so that is, I know that there's a mutex lock. He's given a mutex structure which contains a magic number, and so if I do that and then I continue, then there are all my printfs. It actually is a breakpoint, and I can make it conditional. So I can say condition to, I want actually my magic number is not that, and I can continue. And well, this program is like correct, so the magic number is always that. So my dprintf doesn't trigger, but you understand what I was getting at. By default, what will happen is it will hit that breakpoint, it'll go back to GDB, GDB will figure out what to print, it'll print for you, and then it'll continue. You can use call, so you can, I'll get into some more of this in a minute, but GDB will let you call functions in the inferior, and you can actually tell GDB, don't like try and work out the printf yourself, just call printf inside the inferior and print the stuff. Or you can use the agent, which again, for remote debugging, will cause that printf to happen from like directly on the target rather than coming back to the thing, the host that you're debugging from. So that's that can be really good for performance on, especially on remote debugging. You can tell it to use a different printf function. Maybe you've got your own logging function you want it to call. And the printf channel, that's basically just the argument, the first argument to pass to whatever printf function you've told it to print. So in the case of fprintf, it might be stood out, right? Yes, I mentioned calling inferior functions. So I suspect most people have done this a bit. It's quite useful. Less useful these days now that we've got the pretty printer support. You can do all that stuff in the GDB. The most common place I think people do call is to pretty print some data structure or something. But there are various times when it's useful to do. Sometimes GDB can be a bit clever, right? And tries to do too much for you, in my opinion. So it can be surprising, right? So print foo plus bar, if this is C++ and the plus operator is overloaded, it will go and call that function, right? Print erno will call a function because erno on Linux is a macro which calls a function to get thread local storage, and there's a function call underneath, right? So if, I don't know, my stack is garbage and I try to print erno, might not do what I hope it's going to do. If I pass a string literal, so I'm doing call to strcpy buffer, passing this string literal, first of all, there'll be a call to malloc some memory in which to put the string literal that you don't see, which I can tell you from personal experience, if you're trying to debug your own malloc implementation, is painful. Catch points are very cool. So yeah, we can catch C++ exceptions, or we can catch when the exception is thrown or when the exception is caught. We can catch syscalls, which I find useful a lot of the time. So you know that there's the bad thing is happening around the time that this syscall happens. So I can just put a catch point, and anytime the syscall happens, that'll be caught. So it's sort of doing something vaguely similar to what strace does by using the ptrace syscall command to run until a syscall happens. So that'll catch any syscall. Doesn't matter how the syscall is crafted. You could, if you like, write your own assembly to do your system calls, it'll still work. Remote debugging I talked about very briefly. I think probably if this is relevant to you, you already know the basics, so I'm not going to go into too much detail. Multi-process debugging is pretty good. So I can debug multiple inferiors at the same time. So let's come out of that. So here's my very simple function fork.c. And so if I GDB that, here we go. So I'm going to set detach on fork off. So normally, when you fork, GDB will continue to debug the parent process, and the child process will just be allowed to, off it goes. But if I set detach on fork off, that's not what happens. So when I go next, now I've got a new inferior has appeared. So info inferiors works just like info threads. And so here's my parent. I can see this is the parent. So if I print p, I can see, sure enough, fork has returned non-zero, which it will do in the parent. If I switch, just like with threads, I can switch to inferior 2. Now, kind of inside the libc implementation of fork here, so let's just finish out into our own code. And here I can see print p is 0. So inferior 1, p is non-zero, inferior 2, p is 0, right? And I can attach as well. So I can create a new inferior. So if I go add inferior, and then I'll see I've got this null inferior, which I can switch to. And then let's give it something to attach to. So I'm just going to run sleep 30 in the background like that. Okay, and what do I have? Oh, that's all kind of messed up, isn't it? But it should be, where's, there it is, yeah, oh, it's just page wrapped, yeah. So, line wraps. So if I can attach to that, and info inferiors, and there we are. So that's quite useful if you're debugging lots of things at the same time, which often one needs to do. You can see I've completely messed up my 2E mode here, but Control L gets me back into some sane state. You can choose just to follow the child rather than the parent if you want, and for some bizarre reason you can decide with exec to do the old, still be debugging the old process even when it's exec something new. I have no idea why you would want to do that. I guess somebody at some point did. I can clone the inferior, so it'll do a clone system call, which kind of can give you your own kind of snapshot. Debugging if you want to do that. So you can, this is an interesting point in time, I want to clone that and keep that around so that I can, and so sort of do a fork of that process, and then I can go back to it and see any state from before. You can do your own commands in Python. I'm not going to go into detail on this, but this is useful. And so at undo we do a lot of this, so you can make your own commands to do whatever bunch of Python you want, and you can give it help and all the rest of it. Stop handlers, these can be quite useful depending on what you're doing. You can do them in Python like this, or you can do them in sort of GDB native as well. So you can define a user-defined function for hook stop. So if I go, like for example, define hook stop print PC, and now every time I stop, it's going to print the PC, which it kind of would normally do anyway, but I could do something, I could do whatever I wanted in that hook. So the least amount of typing is to do it with a GDB inbuilt user-defined function. But if you want a bit more power, you need a bit, you want something a bit more expressive, then you can do it through the Python. Other cool things very quickly, temporary breakpoints are breakpoint. So unlike, so this is part of the not great interface. Rwatch is a read watch point. Rbreak is different. It's a regex breakpoint, but if you want to put a breakpoint on every function that starts with myLibrary underscore, you can just go rbreak myLibrary underscore dot star, and it'll put breakpoint on all of those. You can attach commands to run every time a breakpoint is hit. That's probably and then this is just the last bit on GDB, because I find myself saying this quite a lot. The GCC or Clang's -G and -O are completely orthogonal, right? So -G, which gives you your debug info, which allows the debugger then to look at a program counter and figure out what line of source code you're at. That does not change the code generation at all. It just creates these extra sections in your executable file. And if you're not debugging, they don't even get mapped in, right? So it's just disk space and a small amount of compile time to say -G, or in fact -G GDB3, which will be a better dwarf info. There's no pain, there's no cost to putting -G other than that small amount of disk space, unless you actually are debugging it when it'll get paged in. So yeah, often people have debug builds, which is like -G -O0, and release builds, which is like -O3 or whatever, but you can mix and match. -OG is quite good. -OG will do kind of sensible level of optimizations, but not too much mad shit, right? So when you have very tightly optimized code with -O4 or whatever, or even -O2, often you'll find things are optimized away, which is frustrating, or you'll find you step forwards and the thing jumps back over here because the compiler's decided to lay the code out differently and all that kind of stuff, and functions get inlined and it all gets a bit funky. -OG is good because it just like I say, it sort of with -O0 on the other hand, does really does mean no optimization at all, and every single variable that you access will be first loaded and then stored back at the end of the access, and it's all there's just loads of machine code you don't care about. So -OG is a good compromise. All right, enough GDB. Let's do some other stuff. Timer. So Valgrind. Which probably lots of people know about. Just in my experience, it just works. It can be quite slow, depending on what your program is doing. The slowdown can be 10x, 100x maybe. But yeah, it's very easy to use and does just work. And it's very good for finding particularly kind of uninitialized variables and things like that. And also buffer overruns if they are allocated on the heap, not so much on the stack. The simple memory leaks as well, of course. It'll tell you if you've malloped some memory and not freed it. So yeah, let's show that, right? So perhaps I'll give a real story as well of many years ago. I worked at a company where we were making a kernel bypass library for high-performance networking, and the customer gave us a bug report and said, "Well, your stuff's broken because my code works fine without your kernel bypass library, and I use your kernel bypass library and it stops working." And we sort of scratched our head and looked and couldn't get to the bottom of it. And so in the end, wasn't me, somebody very smart there decided, well, let's just run their program without our library, but through Valgrind. And we found, sure enough, there was uninitialized data on the stack being used, and that meant that which they were getting away with without our library, because when our library was there, it moved things around. And the point of that story is we didn't have access to that source code or anything, right? This was a binary from the customer, but it was still sort of a useful way to be able to debug that thing without any, with almost nothing to go on. So here's a little program that just does some uninitialized memory accesses. And if I run that through Valgrind, here we go, tells me about all these uninitialized accesses and tells me where they were uninitialized from, and even gives me a backtrace, right? So that's very useful, obviously. Likewise, it will tell me if there are mallocs that I haven't freed, that kind of thing. I can also use it in conjunction with GDB. There's a Valgrind has its own implementation of the GDB server inside it, which you can then attach GDB to. So if I go Valgrind a.out vgdb, hang on. I think you need to actually give it, I think my slides are wrong, it's full. And this tells it how many errors to step over before. Oh yes, thank you. This is just to prove that I'm not faking anything. Yeah, there you go. So here we are. So okay, this is I'm attaching GDB from the beginning here. So it gives me nice instructions. So to attach GDB, it says I need to do this. So I can copy paste that. Get into a new window here and do that. There we go. Continue, and okay, so there it's hit an error. And here I am in GDB, and I can get my backtrace and poke around and see what's happened, and I can continue until the next one. Valgrind isn't actually the thing that people talk about when Valgrind is actually the memcheck implementation on top of Valgrind. It's more of a kind of platform, and there are various other things like cachegrind or cachegrind, I don't know how you pronounce these things, data race detector, and even none if you want to just check the performance of running the Valgrind sort of engine without doing any checks. I think by far the most commonly used one is memcheck, which you get by default. But yeah, the cache profile is kind of interesting. So it simulates Valgrind actually, it simulates the program, and it does a JIT binary translation of the machine code into a kind of simulated machine, and then it can kind of do analysis on how it would be accessing the cache if you tell it about what the cache configuration is. How big a cache line is, how many ways associative what associativity does the cache implementation have, all that kind of stuff. So a good thing about Valgrind is you don't need to recompile your binaries or anything. You might not even have the ability, you might just have a binary that you're looking at, as I said in that example before. It's very good at finding uninitialized accesses. If you do a buffer overrun on the heap, it doesn't seem to spot it, at least in my experience. Memory leaks. Now, the thing with memory leak debugging, I think all of the tools I've seen that allegedly help you with this, they help with the easy stuff, right? Which is, I just did a malloc. I can see I did a malloc here, and then I've got an error return here, and I don't free in that error return. That's kind of useful, but not that hard, right? The tricky memory leaks are things like when you've got a reference count that doesn't decrement when it should, right? It's kind of I think these tools don't really help you with that, right? Because it's like, yeah, I know where I allocated from, right? The question is like, why didn't it free? It should free here. That's where things like, actually you can combine this kind of stuff with reversible debugging, and you can start to like track through how that happened. I might get to that if we get time. It is, as I said, quite slow, and static local buffer overruns not so good. Sanitizers, address sanitizer being the most well used, I think. Originally came along in Clang, now exists in GCC as well, and works very well. It's almost like it seems to be the opposite of Valgrind. It seems all the stuff Valgrind is good at, sanitizers aren't, and vice versa. So, well, that's kind of good. I guess you pays your money, it takes your choice. Yeah, very fast. It's got good compatibility with other things as well. So you can typically do, as I hinted before, like things like reversible debugging tools with address sanitizer. It's not doing jitting. It's not jitting the code or anything like that. So anything that relies on jitting the code is going to struggle with Valgrind, because the two jits kind of get in each other's way. Address sanitizer doesn't. Of course, you do need to recompile it, right? It's a thing that the compiler does. Does use quite a lot of memory. And I'll come on to fortification in a minute. One thing you can do that's, if you like, it's fast, but not like it's not measurable. So you can set functions to have this attribute no sanitize. If you're confident that you've got some sort of function called in a tight loop that you're pretty confident is correct. So what do we have here? So let's do that. So I think I've got this programs stack, which clearly is not a very good program. So f sanitize equals address. I think on mine, I remember I had to give it this static lib. I can't remember why I needed that, but I think you do need that. Okay, if I run that, so there we go, and it's told me, it's spotted that problem and told me where it's happened. So yeah, as I said, so it seems to be pretty much the opposite to Valgrind, and where it's useful and where it's less so. Fortification is a thing that's in modern compilers and modern C libraries, and it'll do lots of just kind of very lightweight buffer overrun checks. Yeah, it's almost impossible to measure the performance overheads of this. So there's really not a good reason not to use it, frankly, unless you really looking to shave every nanosecond or something. In fact, so much so that if you get, well, I said many modern distros, which is sort of, I suppose the translation of that is on Ubuntu, which I run. I don't know what is on others, but anyway, at least on Ubuntu, fortify source equals 2 is the default, so this is kind of redundant on my line. In fact, if you do minus the fortify source equals 0, you get this, you'll see it, you get a warning. So I just define that, and if I, and then, I don't know, and if I say it to 0, that's interesting. That didn't happen yesterday. I don't know. Oh, maybe it's just because of, no. Don't know. Anyway, it's I'll probably, if I spelt it wrong. Well, anyway, so that's we'll not spend too long debugging that, but yeah, very very useful. Okay, ftrace. So ftrace it's really originally more of a kind of kernel debugging and profiling thing. But it's very useful. So particularly inside the kernel, right? So a lot of what I've shown so far is I have a user mode application that I'm looking to debug, but often some of these hard problems are subtle interactions between the program or programs that are running and the kernel. So here's a relatively recent story of at Undo we're working with a large software vendor who I won't name, and we're trying to get IR Tech embedded into their test suite so that when the test fails, they'd have a recording and they can see exactly what happened. They said, yeah, well, it keeps the thing keeps dying with these sig kills. We said, oh, we've seen that before. This is quite common. You probably have some kind of process killer in your test environment that's kicking in and is causing these problems. And they said, no, we don't do that. It's not that. Okay. So we had more of a think, scratched our heads, came back, and you said, really? Sure you don't have a process killer? No, definitely don't have a process killer. So we gave them a script to run, an ftrace script, which did something that I'll get to in a minute, which told us about all the signals that were flying around. And so we said, there's a process called Watchdog that's sending some signals. And they said, oh, can I let me ask around? I said, oh yeah, that's our process killer. So the script that we did was quite simple, looked something like this, right? So I'm going to become root. Oops. Oh, wish I hadn't done that, right? So I can never remember this, right? So give a condition, so signal more than, so any, I want to trace all signals, and I'm going to put it in sys kernel debug tracing. So that's how I'm going to filter out, what have I done wrong there? Debug tracing events, signal filter. Tracing events, signal filter. So I'm interested in all signals here. I'm going to turn it on. Sys kernel debug tracing events signal enable. No, meant that. And then we just need to turn it on. Sys kernel debug tracing on. And now, if I just have a look at the trace, proc kernel sys kernel debug tracing trace. Here I can see all the signals that are flying around in my system. Lots of SIG-17s, which is SIG child, so that's kind of expected. SIG-14, I think, is a SIG alarm. This is useful, right? I can see which process is emitting the signals, which process is receiving the signals, whether they have a signal handler, all that kind of good stuff. I can clear the log just by writing something. So if I just write anything to that, then it clears the log. And so now I can see those signals starting to, well, these are all signal 17 by me running cat, of course. And you can do all kinds of cool stuff. You can also use the trace command tool if you don't like poking around inside the sys file system. So let's have a look. Yeah, so let's sys kernel debug tracing, available events. So these are all the kind of pre-installed hooks inside the kernel, loads of file system stuff. Let's have a look, see if we can find some networking stuff. Here we go. So I could look for retransmits of a synac, for example, if something weird. And let's just, because this is easier to demonstrate, let's pick destroy sock. So if I go trace command, going to record, give it an expression of looking for those. And now let's, I don't know, let's go try and create a socket. Okay, that doesn't seem to be connecting, whatever. So now we can, so if I go trace command report, there we go. So there's my destroying a socket operation to address 8888. So I can pull all kinds of useful things out of what my system is doing with ftrace. Strace, I suspect, or strace, I suspect we all know. but very useful if you just want to get that first kind of level of like what's going on. There's perhaps a bit more to it than just the simple, obviously there's strace command. So again, this is using ptrace just like GDB does. But this can be kind of useful, right? So where are these system calls coming from? Strace-k, prefix them, put file, obviously. Follow forks, that can be very useful. And I can attach to processes as well. I'm not going to show examples, so I think it's quite straightforward. ltrace, which is like strace, but for libraries. So it's printing all the library calls, right? So if I go, I don't know, ltrace ls, I can see all of the library calls. So I said I was going to show strace, but let's just compare, right? So strace, that's all my library calls, on all my system calls. ltrace, on when I run ls, gives me all my library calls. Can get backtraces. Now, unfortunately, only if ltrace is compiled with libunwind, which on my distro it's not, so that doesn't work, but would be cool if it did. You can kind of filter on certain libraries or certain functions in certain libraries, so very useful to see what's going on. As perf-trace, which is kind of an alternative implementation. So strace, as I said, it's built on the ptrace API, so it does a very similar thing. You know, it runs the thing, the tracee. Every time something happens, in this case it's a system call or receipt of a signal or something, there's a context switch back to strace, it does some stuff, and then it continues, right? So it's pretty slow. Perf-trace is much better performing, and you can even just like run it like that, and I can trace every process on the system. So this is kind of your equivalent of strace using perf. So let's see what happens if I go perf trace ls. Is that going to do? There we go. So I can see it's kind of similar, but it's not. It's just a completely different implementation, and it's going to be a lot faster. There are some things it lets me do that the strace doesn't, and vice versa. So these things often, as always, it's not a complete substitute. But you need to be root. And it doesn't do as much decoding. strace does quite a good job of telling you like what the arguments to your system calls actually are, whereas perf-trace will just kind of give you raw pointers and things, which is often a bit of a pain. But anyway, there's also, this is quite cool, this is perf-pt, so the processor trace. So this is an Intel thing. So Intel, actually the earlier Intel CPUs, going back sort of 5-10 years, they had this thing called the branch trace cache, BTS branch trace store, and that would store the address of the target address of every single branch that the processor did in a buffer. And you could, until recently, use perf to get that information out. For reasons I haven't looked into, but if you need the kpti workaround for Spectre Meltdown and all that stuff, where the kernel has different page tables, BTS doesn't work if you haven't disabled that. I'm not sure whether it's felt that was another attack vector or something. I haven't looked into the details, but basically, your system almost certainly is running with kpti, hopefully, and so BTS probably won't work. But PT, which is kind of the successor, processor trace, which is like the newer, better thing than BTS, does work. It stores basically a bit for most of the branches. It just stores a bit that tells you that can be used to tell you whether or not the branch was taken, rather than just. I guess for indirect branches it does store the target of the indirect branch, although I don't actually know. But so we can do that. So PT, so Intel PT //u for just the user space part. So perf record. So Intel PT. So if I run it like that, and then actually let's do it with my program so that. And so now I can go perf. I'll perf report. So this is, as I say, more. This is like the view that's more commonly used for profiling, which isn't actually what I want to do here. So if I run perf script, now I can see here all of the branches in my program, which is quite good. Doesn't, it's not, doesn't give me kind of reversible debugging as in the sense that I can't go back and see my program state. Actually, although I've never used it, I believe that modern GDBs have this support, so you can actually navigate through history from using the processor trace from within GDB as well. So let's go now to the bit that's sort of closer to my heart, so reversible debugging. So what as I said before, what do you want when you're debugging? You're looking at like reality diverged from my expectations. My program didn't do what I expected it to do, and I need to figure out why. I need to know when did that divergence happen, and why did it happen. And so reversible debugging is a thing that we do at Undo, and there's a number of other implementations as well. The GDB inbuilt, this slide's a little bit old actually, the GDB inbuilt reversible debugging actually doesn't work quite so well now because I don't think it's actively maintained, and some of the newer instructions are not supported. So things like modern libc just won't start. But yeah, I should say it's called btrace, which uses the branch trace, but only if you don't have kpti. But let's look at this. Let's look at what this is. Take a seat. So let's come back. So I have a program that's a bubble sort, and if I compile it, if I run it, it doesn't actually print any output; it just sorts the stuff. But I happen to know why I don't do echo. If I run that in a loop enough times, right? I've got stack smash now. Actually, I'm going to show you this. So combined with the fortify stuff, modern distros have some stack smashing stuff built in, but that's actually going to defeat me. So I'm here. So I'm going to turn that off. No stack protect. And I think just for no stack protect all, I'm going to do it like that. So if I do it like this, let's just make sure it fails in the right way. As always with debugging, when you want the thing to fail, it's not going to do it. I'll tell you why that is. I think I've just remembered what I did wrong. I think it needs that. Yeah, okay. So I've got a core dump, all right, so let's have a look at that. Okay, so let's load up my core dump. Backtrace, absolutely no help whatsoever. So I just jumped into hyperspace and I don't know why. So I'm going to run this inside GDB. I'm going to use the inbuilt reversible debugging, which is just slow but demonstrates the point, demonstrates what we want to see, and some other stuff as well actually. So it's not a bad demo. So start the program. So whoops. Right, let's do this properly. Right, start the program. So what I'm actually going to do, I'm going to put a break. I need to enable recording. Right, by default recording is off. I just enable recording like that. Continue. It runs. The only thing is, this is one of those intermittent bugs. So I'm going to have to do that a lot of times. So I want to script this. So what I'm going to do is I'm going to put a breakpoint on main. I'm going to do some commands on that breakpoint, which is to enable recording and continue. I'm going to put another breakpoint on exit, and I'm going to put some commands on that, which is just to rerun the program. And I'm going to make sure I've got pagination off, and I'm going to make sure I've got confirmation off, and then I'm going to continue, right? And what this is going to do is just run the thing again and again and again while it can with recording, and if we wait long enough, eventually, maybe we'll come back after lunch. Come on. Sorry? Do you think it's not? Oh, look, I've just killed GDB. That's good. Okay. Yeah. Oh, man. That just feels like it was the beginning of a really, really slick demo. Well, I'd now go in and debug GDB, but like next time. Right, break main. So you think I got this wrong? Record, continue, end, break on exit, command 2, run, end, set confirm off, set pagination off. Yeah, that's running much more slowly, so I think that probably has done what I wanted it to do. So we can see how much, so we can see, get a sense of the slowdown of GDB inbuilt process record. What it's doing, much like software watch points, is it's single stepping one instruction at a time and recording what changed. But that'll be enough, hopefully. There we go. Right. So it's died, backtrace, useless. Reverse step I. I'm going to step back one instruction. And now, we've gone into something that's a bit more useful. Right, so if I disassemble where we are, so I can see if I disassemble the current function, see that little pointer thing there, tells me this is the current instruction. It's on a return instruction, so my return instruction appears to have gone into hyperspace. Let's see, so the return instruction will jump to what the stack pointer points to. So stack pointer points to that. So if I examine the memory at that address, that looks, well, okay, let's try something. Let's print star unsigned long star of stack pointer, and yeah, that doesn't look like an address. What's there? Okay, let's examine that. That memory, so that what that's telling me, somewhat unhelpful error message, is that address doesn't exist. So my stack has indeed been corrupted. So what I want to do is, obviously, it's like, well, why did that happen? So I'm going to set a watch point, and I'm going to watch that address. That's the stack there. And I'm going to reverse continue. So let's do it in full. So reverse continue. So I'm going to run backwards until that watch point is triggered, until that stack location changes. It's gone back to beginning. That's not supposed to happen. What did I get wrong? Reverse step I. Print stack pointer. Info break. All right. Well, that seems to have rotted. That demo used to work. What that would... let's see if I can do this. All right, I'm going to go completely off-piste now, and I'm going to do this another way, which is to run it inside... let's use. I don't know if this is going to work, but let's try. Let's use RR. So RR is a much faster record replay tool. It's a separate step of recording and then debugging. So if I run it like this, there we go. Now if I RR replay that, just to make sure that this works. Yeah, that all looks good. So let's run that in. Let's go. Let's see if this works. Okay. So this is just filling up my files. Okay, there we go. So now let's see if we can replay that. Okay, so I'm at the beginning, so I'm now going to continue. Just run to the end of my recorded session, hit that segfault, just like before, garbage stack, reverse step I, and quite get to where, okay, I did a couple of those. So here we are. So what's the stack pointer? Stack pointer now is that. So let's watch, so long start of that. And now let's reverse continue. See if this does better. Yay, that's worked. Right. So this is now setting, so what's happening? Okay, well, I'm writing into my array, and that appears to be writing onto the return address in my stack, which almost certainly is not what I wanted. I can have a look at my local variable. So I is 35. I think if I go what is array in GDB, it can tell me the type. So it's saying, yeah, it's an array of 32 elements, and I'm accessing the 35th element. So that's not so surprising that that's bad. Well, why has that happened? Well, now I can see if I just look here, I'm actually percent size of array. So of course, print size of array is 256 because it's the number of bytes, not the number of elements. So there's a nice example where we've got intermittent failure. You know, intermittent failures are hard to debug, right? Because typically you need to rerun to extract more information. With these kinds of with these tools, with GDB inbuilt reverse debugging, with RR or with our stuff from undo, what you've got is essentially like full content. You can go back to any instruction that executed, and you can see the full program state. Right, every local, every global for any instruction executed. So there is now nothing about my program's execution that I can't just go and see, and I can do things like set watch points and go back. Let's show. Because it's a little bit too generous just to show all this stuff and not show ours. So let's show this on a bigger process. I'm going to fire up LibreOffice, so I think it's cool. So that's the thing I've just started. So I can attach to that with Live Recorder. I can just attach to that process, and just okay. And I can see now if I try and type, it's like a little bit slow, but basically works, right? And actually, because what we're doing is this JIT binary retranslation of the code underneath, so the caches all get warm and it gets quicker. I know it's like save as, and I can see it's taking a little while, but you know, it's basically, there we go, control under that. Don't save. And so that will have written this this event log. And I can load that up into when it's finished doing its thing. So Live Recorder does it all in memory and then dumps it out at the end. We compress it as well, so it's going to take a little while. But anyway, that will do, and then I can load that up into our debugger UDB and do the same kind of thing. So different ways to do that. As always with these tools, there's different pros and cons. You pays your money or not, and it takes your choice. Very quickly, because we're just running out of time, as our good friends JetBrains are outside, and we tool vendors should look after each other. Here's CLion, which is a C++ IDE. We have a plugin for this as well, so you can run our stuff with it. And it's got lots of cool features. I mean, if you want to know all the CLion features, go and see the JetBrains guys outside. I have heard from some of our customers who have very large code bases that it doesn't always scale. If you've got loads, like millions of lines of code, it can be a bit slow. But for kind of anything but the biggest projects, I think it works very well. Loads of cool kind of time-saving features to transform your code and debug in various ways, including our undo plugin, which you can see running there. So that kind of just about gets us out of time. A few minutes left. If there's any questions or comments, yeah. I think so. Oh no, it's LD preload stuff, isn't it, to get working as well? I think. Yeah.
If it was updated, turn tracking on off using code, it works.
Yeah. Yeah, so we get the same actually because of the way our stuff works. We're just looking at non-deterministic inputs to the program and relying on re-execution. So we often get told, yeah, can we turn recording on and off? And you can, but it's almost certainly not what you want because it'll end up having to you'll end up with a lot more, actually tracking a lot more state because you don't know what's happened. You can't rely on the re-execution. Yeah. Yes?
You mentioned in an earlier slide that the rapacious owners of undo charge a very expensive price for the product. What is that price?
Of what, sorry? Of like?
The undo software.
The undo software, oh right, yeah. I get into terrible trouble when I talk about pricing. So you have to, yeah, I'm not going to get into that, especially as it's being recorded. talk to me later. Any others? Yeah.
You've got all C++ debugging techniques in GDB when you're in boost or something, you end up getting 500 lines of template printing stuff every time you use it.
Not directly, but I'll throw it out to the audience, given all the people in the room. Anybody got any? So the question was, if you're debugging some, boost or something, and loads of templates and printing stuff. The problem is printing stuff out in this very templated world can just give you pages of output because it tries to sort of expand all of the template stuff. Anybody, any tips for dealing with that other than try to stay away from templates? Yeah.
Have you, if you want to sort of improve your debugging skills, have you come across any good sort of modern references?
No, and I think that's got a part of why I do this talk and these talks, right? Is I think it's really strange when you compare it to how much stuff out there on profiling or all kinds of stuff, or learning new languages or whatever it is. Like there's always loads of resource out there. For debugging, it's like we're all kind of to some degree on our own. I'm sure there is good stuff, and again, I'll put it out to the audience if anyone's got any suggestions of references for just how the hell do you do debugging? Yeah, I mean there are some books, although the ones I know of are all quite old now. They're probably good. Probably all good, probably the stuff's all still good. But yeah, it's one of those. Do you know what? I wonder whether it's one of those things that just because it's too hard. Like profiling is. Am I going to get in trouble for saying this? I'll say it anyway. So profiling, I think, is an easier problem, right? It's easier to talk about. It's easier to sort of have tools that tell you what you need to do, and so there's lots of stuff around it. And I think for the problems that are really hard, we're all kind of, I don't know. Maybe it's good for job security. Perfect. I think I'm going to stop it there because I don't think I'm going to get any better comments or questions than that. So thank you very much. I'm hanging around at the Undo booth today and tomorrow, so maybe see you later.